Alrighty, in question number 34, it says a record of travel along a straight path is as follows. Starting from rest with a constant acceleration of 2.77 meters per second squared for 15 seconds. Part 2, constant velocity for the next 2.05 minutes. Part 3, constant negative acceleration for negative 9.47 meters per second squared for 4.39 seconds. A, what is the total displacement for the complete trip? B, what were the average speeds for legs 1, 2, and 3 of the trip as well as for the complete trip? Okay, here we go. Based on information in part 1 and 2 and 3, we need to identify the concept in this problem. Well, it mentions explicitly that there's constant acceleration in part 1 and part 3 and constant velocity in part 2. So we need to be looking to use both of these concepts as we do this problem. Remember, with constant acceleration, we have 4 possible equations we can use depending on the variables that are present. If the variables v, v naught, a, and t are present, we can use the first equation. If the variables x, x naught, v naught, a, and t are present, we can use the second equation. If the variables v, v naught, a, x, and x naught are present, we can use the third equation. And if the variables x, x naught, v, v naught, and t are present, we can use the fourth equation. Another way to look at it is which variable you don't have. Well, if I don't have x, right, then I can use this particular equation here. If I don't need velocity and I don't have velocity, this equation doesn't have velocity. This equation doesn't have time, and this equation doesn't have acceleration. So that's another way to think about it as you exclude equations from use and actually be able to choose the right one. This is also a segmented motion problem, as in motion starts off one way and then continues another way and then changes to yet a third way. So we should do and sort out a segmented motion problem by charting it up. So part 1. Part 1, we are speeding up with constant acceleration. I abbreviate CA for constant acceleration. Well, when we have our constant acceleration concept, we're going to begin by listing our variables. Our variables would be x, x naught, v, v naught, a, and t. And since this is all part 1, I'm going to give these all little subscripts just to kind of separate them from other parts. Now, reading the problem, it says starts from rest. Well, when we see that phrase, v naught, the initial velocity, equals 0. That's something to file away as we do our problems. It also says with constant acceleration of 2.77 meters per second squared. Well, anytime you see the unit of meters per second squared, that goes with acceleration. 2.77 is the value for the problem. And we're told this happens for 15 seconds. So the first thing you do is label your 6 variables, then you go back and reread the problem to label the information that's given. Now everything else must therefore be an unknown. Some unknowns are relevant to the problem, some unknowns are, they just really don't matter. So what we're going to do in this case is we're also going to make one assumption here, since the problem doesn't tell us where the vehicle or object or person is starting. I'm assuming it's a vehicle because these are pretty fast speeds for a person. We're going to assume the initial position of 0. If it doesn't tell you otherwise, we're starting from an initial position of 0. We do not know the final position, so I'm going to put a question mark next to it, nor do we know the final speed in which we accelerate to. Put a question mark there. The next thing I'm going to do is I'm going to chart up the second portion of this, part 2, constant velocity. Now, constant velocity, I abbreviate that one CV. Now with this one, we have far fewer variables. Okay, for this one, we have x and x naught. So we have delta x for this first part here. And by the way, what we can do to simplify this problem a little bit is we can not necessarily worry about individual positions, and we can focus on just a displacement overall for that particular segment of motion. That might be an easier way to handle the tidiness of the problem, I guess you would say. But the three variables involved would be your displacement, your velocity, and your time. Okay, in which case I'll call delta x2, v2, and t2. Now it tells us that we have constant velocity for 2.05 minutes. Now I can already tell you this is going to be a problem here with a unit of minutes and units of seconds over here. So we're going to have to change out that second unit of minutes to seconds, but we'll do that in a short time. The other thing we don't know is we don't know how far we went, and we don't know how fast we're going during this segment. But here's what we do know. Segment 2 immediately follows segment 1. Therefore, the speed we accelerate to, this right here, really becomes the same as this constant velocity right here. Something to keep in mind as we do the problem. And then the third segment of motion is our constant negative acceleration, our slowing down part. Now we know it's slowing down because we're still moving forward and we have negative acceleration to account for it. So slowing down, moving forward accounts for negative constant acceleration. Constant acceleration nonetheless, therefore we will list those same 6 variables. X, x naught, v, v naught, a, and t. Now, for this one, again, we don't know how far we went. We don't know how fast we're going when we slow down to a certain speed, but we do know that it happens for 4.39 seconds, and we do know the negative acceleration applied is negative 9.47 meters per second squared. Now, we also do not know the initial velocity for this third segment, but we do know this. Whatever constant velocity we have for the second leg here, that becomes the initial velocity for the third part of this problem. So that's one thing to always keep in mind. When we do a segmented motion problem, the velocity at the end of one segment becomes the beginning velocity at the next segment. The position where we end up at the end of one segment becomes the initial position of the next segment. Okay? Or what you can do, and I tend to find this easier, is you can simply make the initial position of each segment 0 and just focus on finding the displacement or the final position of each one of those segments and then simply add them all together. That can be an easier way to deal with it. And I tend to deal with it that way more often. So many times I just don't worry about the initial position. Now, in part A, it's asking for the total displacement of the trip. So in order to find the total displacement, we need to add up our displacements for segment 1, segment 2, and segment 3, which means we need to find them. So if I take a look at the variables that we have here, okay, and let's take a look at for displacement, okay, in segment 1. And let me go ahead and get rid of that. If I'm trying to find displacement, I'm trying to find that final position, I'm looking for an equation that has x in it, okay? So I could either use this equation, or this equation. All three of them have x in it. Now you'll notice that I have acceleration given in the problem. Well, the fourth equation does not have acceleration in the problem, so I'm probably not going to use that. I also should notice that I have time given in my problem, 15 seconds. This third equation does not have time in it, so I can't really use that. What I can do is I can focus on the second equation, and that's the one I'm going to use. x equals x naught plus v naught t plus 1/2 at squared. We know the v naught is 0, so 0 times time zeroes out the middle term, initial position of 0. And that leaves us with x equals 1/2 at squared. Let's fill that out. 1/2 times 2.77 times 15 squared. Now when we fill this out, square the 15, multiply times 2.77, then take half. And if we do this correctly, we should get about 312 meters for the first leg. Now the other thing that would be handy to find before we move on to part 2 is the velocity that we accelerate to, simply because that's the constant velocity of the second part of the problem. So we should find that. Now, how could we find the velocity of the first segment? Well, notice, ladies and gentlemen, we're looking for the final velocity. We have the initial velocity is 0, we have acceleration, and we have time. We could therefore use the first equation listed here. V equals v naught plus at. Cancel our initial velocity. And 2.77 times 15 gives us roughly about 41.6 meters per second. So this becomes our constant velocity for part 2. Okay, so here's what we know so far. For part A, we know that delta x1, the first displacement, is 312 meters. Plus, we need to find for segment 2. Now, delta x is equal to velocity times time. So, velocity would be 41.6 meters per second times, see, there we go. Okay, we have meters per second, but we're trying to multiply that times the time in minutes, and that's not going to work. So what we do is we multiply by a conversion factor of 60 seconds in 1 minute. Okay, so multiplying 2.05 by 60, and we get 123 seconds, which will cancel effectively there. And we get about 5,117 meters for segment 2. Now for segment 3, we need a formula that's going to allow us to find the displacement after 4.39 seconds. Now, we can go back and use that second equation again, but this time something's going to be a little different about it. X equals, and then v naught t plus 1/2 at squared. Again, I'm not including the x naught term in here. The x naught term is really combined in this part right here. So I'm not really going to talk about it, but then I'm going to add my delta x's together when it's all said and done. So I'm going to plug into this. My initial velocity is the same as my constant velocity of 41.6 meters per second. 41.6 meters per second. Times 4.39 seconds plus 1/2 times negative 9.47 times 4.39 squared. Now, breaking this down, if I multiply 41.6 times 4.39, I get about 182.6. And if I square the 4.39 times negative 9.49 and take half of it, I have about 91.25. Subtracting these, I get about 91.3 meters. Adding my displacements together, I get a total of 5,520 meters for the entire journey. Now for part B, I need to find the average speeds for leg 1, 2, 3, and the entire trip. So the average velocity, the average speed for leg 1 can be the entire distance of leg 1, 312, over the time it took to travel leg 1, which would be about 20.8 meters per second. The velocity for segment 2 is a constant flat velocity of 41.6. So the constant speed is the average speed. The average of 41.6 and 41.6 and 41.6 all the way across a 2.05 minute interval will of course be constant. And the third leg would be 91.3 meters in 4.39 seconds, which also gives us about 20.8 meters per second. Lastly, to find the average speed for the whole trip, we need the total distance. In this case, since you're moving forward in the positive direction, it's the total displacement as well, divided by the total time. Now the total time, you have to add it up. It's going to be 15 seconds plus 123 seconds plus 4.39 seconds, and we get about 38.8 meters per second on average for the entire trip.